welcome to my talk. I'll be talking about finding and understanding miscompilation bugs in the Solidity compiler. So essentially what a miscompilation bug is that you give an input program to the compiler and it generates code, but the code does something other than what is intended by the programmer. So let's get started. Let's dive right into a piece of YUL that I show in this slide deck. YUL is essentially an intermediate language representation that's used in the Solidity compiler. We have a simple function that accepts a single input parameter and outputs a single value. And the output is supposed to be the nth most significant byte of the constant value 31. And in the global scope, we invoke this function on the input value 1 and store this output value into the storage slot 0. Now, a quick poll, how many of you expect this to store 0 in the slot 0? And how many 1? Okay, maybe it's a little too hard to run through the code right away. So let me try to step through it a little bit. So what the byte opcode does is essentially it indexes the nth byte. So n is the first parameter. It indexes the nth byte of the second argument. The second argument here is the constant value 31. So essentially you're asking the compiler to generate code that says, hey, what's the nth most significant byte? And the most significant bytes are indexed from 0 to 31 because it's a 32-byte word. So you would expect the 0th most significant byte to be the most significant byte and the 31st most significant byte to be the least significant byte. So essentially you're asking the compiler to generate code that would determine the second most significant byte because we index from 0. So the second most significant byte of the constant value 31. And as you can imagine, 31 is a small number that fits into the least significant byte alone. So all of the preceding most significant bytes would be 0. So you would expect the compiler to generate code that would store 0 to storage slot 0. In other words, it should leave storage unchanged. But if you were to use Solidity compiler versions 0.5.5 and enable optimizer, this would actually store 1 to storage slot 0. So clearly there's a problem. It's stuff like this that we set out to find. If you're curious what's happening here, what happened was that there was an optimization rule that was targeting accessing the 31st most significant byte of any constant value. So imagine that you have a big number and you want to access the 31st most significant byte. And the 31st most significant byte happens to be the least significant byte. So what this optimization rule would do is AND that value with the mask FF standing for 255. So you could simply mask the large 32-byte word with 255 and replace the byte with that. But instead of targeting the 31st most significant byte of constant values, it targeted the nth most significant byte of 31 constant values. So essentially, it targeted the wrong input argument of the byte opcode. And this led to a code like this that would be silently, essentially, you would get wrong code generated silently for input programs such as this, which is quite dangerous. But fortunately, there was, in the previous talk, Hari already mentioned, great talk, Hari, that we actually don't have evidence of code gen bugs like this being exploited in the wild. So this was found after a few months after this code was introduced, and fortunately, we got away with it. So the way we find bugs like this is by essentially writing a fuzzer. I call the fuzzer Solsmith after C. Smith, which did something similar for C compilers. So it roughly has 3 components. A program generator, which generates semantically valid but randomly generated programs. And you have an execution tracer, which runs these programs on an EVM client and produces an execution trace of the code. And you have the test harness, which instruments the setup. So essentially, what we could do is have a baseline and then an experiment and tweak a parameter so that we could stress test a component. For example, if we want to test the optimizer, we would essentially use no optimization as the baseline, optimization enabled as the experiment, and any trace divergence between the two would be classified as a bug for later triage. So I'm going to be talking a little bit about the kind of bugs that we found. Two examples. I hope I can get through them. If not, I can skip to the results later on. But let's get started. Hari already mentioned this K-Chack computation bug. Essentially, if you look at this code, what it's doing is that in inline assembly, it is performing two K-Chack computations and assigning it to two Yule variables A and B. Both K-Chack computations are identical. I mean, you probably wouldn't have code like this in the wild because it's wasteful in terms of gas. Bear in mind that K-Chack is gas intensive. It, I believe, takes over 30 units of gas. But let's suppose we had something like this. The compiler tries to essentially optimize K-Chack calls because it's gas intensive by analyzing if the memory regions over which K-Chack hash is computed is identical. And if it is identical, we could cache previous computation and simply use the value that was returned in an earlier computation. It makes perfect sense and it saves gas. So that's how caching works. Now what happens when caching goes wrong? So here you have a slightly altered code snippet compared to the previous slide. The second K-Chack computation is over a subset of the memory region of the first computation. So the first computation is over the first 32 words, and the second computation is over the first 32 bytes, and the second one over the first 23 bytes. And since all the 32 bytes are 0, that's because we did an mstore 00 right in the beginning, you would guess that A and B are not equal because hashing 23 zeros is different than hashing 32 zeros. But the compiler actually said they're equal. And why is this? It turns out that the caching was not strict enough. So it would compare the start pointer of the caching memory region, in this case both start at 0, and only compare memory regions as multiples of 32. So if you have a smaller memory area, so in this case 23 rounded to the nearest multiple is 32, and the compiler would assume that the two K-Chack hashes are starting at the same place and are going to compute for the same length of bytes, and hence they should be equal. And this was a pretty serious bug, but again, we didn't find evidence of this being exploited in the wild. And the fix was rather simple. It is simply that be more aggressive or be more cautious in reusing cached values and make sure that the memory regions are really identical. It's better to err on the side of caution. It's okay if sometimes you have to spend more gas than return a wrong value. The second case study is this bug that had to do with optimizing multiply by 2's exponent. So essentially, if you have two expressions x and y, and then you have a computation such as x multiplied by 1 left shifted by y, in other words, x multiplied by 2's exponent, exponent being y, this could be simply replaced by x being left shifted by y, because multiplying something by 2's exponent is equivalent to left shift by the exponent. The logic here is to essentially save 5 units of gas. So on the left hand side you see the unoptimized version, and on the right hand side you see the optimized version. And the difference in the gas consumption on the two sides is that you save 5 units of gas that goes towards multiplication. That's the idea. But what happens when certain corner cases are not accounted for? Here we have an example. I think it's a little tedious to go over it, but the basic idea is that you have a Yule function called op, which multiplies two values, and these values are obtained by essentially computing a user-defined function called read value and write value. Bear in mind that in Yule, which is the intermediate representation in Solidity, the order of evaluation is from the left to the right. So how this would be evaluated in the function op would be you multiply the the value returned by write value. So you invoke write value first, and then you invoke read value, so that storage is altered in sequence, and essentially the read value returns the value that was written by the write value function. So the correct computation would look like this. We write 2 to storage, and then we read that storage subsequently. So you multiply 2 by 1 left shifted by 2 times. That is, multiply 2 by 4, and you're supposed to get 8. This is the right computation. But if you enabled optimization on the buggy compiler version, what would happen is you would actually get 2 instead of 8. And this is because the optimizer essentially swapped the order of arguments. So write value appeared left in the unoptimized code, but now, because write value and read value are swapped out, and computationally it's supposed to be sound, but what it doesn't take into account is that user-defined functions can have side effects, and these side effects are also dependent on the order of evaluation. So essentially the order of evaluation was not taken into account. So it is bugs like this that we've been able to find by differentially fuzz testing using a tool we call SourceSmith that generates valid programs. We've looked at 2 case studies, but now I'm going to summarize the kind of bugs we found, a quantitative analysis. So if you were to essentially sort the bugs by component, group the bugs by component, then you'd have most of it in the optimizer, some of it in the code gen, and in probably type checking or something would be the rest. So most of it is in the optimizer. But if you look at the severity that was assigned to these bugs, you would find that most of them do not have a rating, and this is because these bugs were found even before they went production. So this actually didn't affect end users unless they were willing to do some risky things. It just goes to show that the impact on code in the wild is pretty slim, although you see bugs with a high severity rating. These require a lot of different conditions to be met to be actually triggered, and the fact that we didn't get a report externally, this was a 0 day, so to speak, by the fuzzer, and no one else ran into this, goes to show that they're actually quite hard to trigger and hard to exploit in the wild, because we actually don't have evidence of it being exploited in the wild. So we would take that as a positive, although the fact that we found 26 bugs initially sounds a little concerning. If you were to group it by impact, only 9 of them actually hit production, and most of them were in this experimental, let's say, component that wasn't the phase of being transitioned into production. So we kind of tested these components pretty early and teased out corner cases and essentially made sure that bugs don't endanger production code. So in summary, the differential fuzzing that we've undertaken is quite effective. Some of the bugs have been even found during code review, which is promising. The Yule optimizer, which started out as an experimental optimizer step, fuzzing has helped transition that safely to production, and 14 bugs were in fact found in the Yule optimizer, but when it was still in the experimental phase. And ever since it's gone production, I would say almost nothing has been found in it, maybe 1 bug. And we've had 0 bug collision with external users, so there's no evidence of these bugs being exploited in the wild. So we found a total of 26 miscompilation bugs. They sound serious, they're definitely serious, but again, they've been found early, which has helped soften the impact of these bugs. We've been able to safely transition the Yule optimizer from experimental to production thanks to these efforts. And the cost-benefit analysis seems promising. We rented out a cluster, which has costed about $15,000. And on average, if you say, if you count the number of bugs that had a severity rating, it would roughly amount to $1,000 per bug, which is quite cost-effective. So yeah, that sums up my presentation. Thank you for your attention.